We had some great questions in the question box this week. The first one is, I've read that katydids can get upwards of 150 kilohertz. That's higher than most bats. How do you filter these out, or are you stuck with them as noise? Well, for those of you that are not familiar with katydids, they're kind of like grasshoppers. They look like this here. They're certainly in the grasshopper family of world. Or for those of you that are not familiar with katydids, they kind of look like this. They're kind of related to grasshoppers, and they look a lot like them. Just for amazingness here, they sometimes can get very big. I think these ones were listed as being from Malaysia in my Google image search, but they're often much smaller, of course. But they're amazing little critters, and they rub their wings together and make noise. And here is an oscillogram on top that's showing you the amplitude, how they're pulsing there. Maybe it's as they rub together. Each rub might be one of those little pulses there. And then here we have the spectrogram with the frequency in kilohertz from 0 up to 125 kilohertz. And the time here, it looks like it's 0.1 seconds that we're looking at. So we're looking at 120 milliseconds here. And the first thing you notice is that these go up all the way up here to, looks like 96 kilohertz, and they just sort of die off. And so the first question we should ask when we see that is I wonder if that has to do with the fact that they don't produce any frequencies up here, or is it an artifact of the microphone, of the recordings? What is that frequency of 96 kilohertz? That's like half of 192 kilohertz, and 192 kilohertz is a common sampling frequency for microphones, for bat microphones to be recording at. And you remember the Nyquist frequency is the maximum frequency that you can detect with your sample rate. And if you're sampling at 192 kilohertz, you can only see signals up to 96 kilohertz. And so even if there is energy above that, you wouldn't be able to see it. So we aren't sure what the sample rate is because I haven't shown it here. It probably says it in the paper, but we could check that. But that would be the very first thing we'd wonder is when we see the signal going off, is that because it's not there, or is it because of the artifact of the way we're recording it? And you could look at the same thing down at the bottom. It seems to sort of start rather abruptly down here at the bottom. Is that because they filtered out lower frequency noises? Or is that because they don't make noise at those lower frequencies? So something to consider. All right, let's take a look at these katydids a little bit more here. This is a slightly different view of the katydid noise. This black curve here shows it's called the power spectral intensity here. And so here we're looking at those same frequencies from 0 up to, in this case, 80 kilohertz. And the relative intensity is on the vertical scale here. So this black curve here is kind of like what the average is across this whole area here at different frequencies. So you sort of draw a line like, where is most of the energy? It looks like most of the energy is in here at this, between 30 and 50 kilohertz. So let's go back over to here, and between about 30 and 50 kilohertz is where this curve is the highest. And there's a little low window here, about 50 kilohertz. If we go and look at 50 kilohertz, looks like maybe there's some less energy there. I'm not entirely sure, but you can kind of see how it gets higher. Here at the 60 to 75, there's this little stripe of more intense energy. Well, that little stripe of more intense energy right in there corresponds to this little bump in this power spectral intensity. So that's black lines, the katydids. There are 3 common bats in the area that this study was done, and one is called the black-bearded tomb bat, and it has lower frequencies that are in like the pink range here. The Java pipistrelle bat is here in the middle, and the bent-wing bat. And so our question is, do the katydids affect the bats? And so this is a study that they did where they're trying to check that out, see if the katydid noise affects bat activity. And what they did was they set up in a rice paddy where there often are katydids. They put all these speakers. Every one of these poles has 2 speakers on it playing katydid noise. They have a special microphone that recorded the katydids, and they play it back through a special speaker that plays back the ultrasound. And then the question is, what happens to the bats? Do they have more? Do they come by more often, less often? Are the bats attracted to the katydids, so avoid the katydids? And so what we're going to do is we're going to look at the results. And they kept the results separate for each of our 3 categories here of bats, the black-bearded, the Java pipistrelle, and the bentwing. And what they're showing here is a correlation coefficient from a linear regression. And that is where you can take a whole bunch of different factors and throw them together and ask the computer to look through statistically and see which ones of those actually contribute to the final result of how many bats they saw of each type. So they have a measure of how many bats they recorded, and they're trying to figure out, can they predict it based upon whether or not the sound was playing back? They also measured the number of arthropods that were there each night and checked to see for a bunch of different nights how much the insects mattered. If there were more insects, you might presume there might be more bats. This is a rice paddy, and so they did this over a number of days, and they figured, well, maybe it has something to do with, bat activity might have to do with when the rice was planted. That might affect, food availability for insects and other things, and so, they'll just keep track of that and see if that makes a difference. And temperature. And, we've talked before how bats have temperature preferences, and so how much will that affect things? And so they do this over many nights, and then what they're showing here is what the best estimate of the correlation coefficient is. So 0 means it has no importance at all. A positive correlation coefficient means it matters, it makes a difference, and when you increase that parameter, you also increase the number of bats. A negative side here means that if you decrease that parameter, you have less of that. So like if you have fewer days since the rice was planted, if the temperatures are cooler, if there were fewer insects collected, or there was no playback, that then would you have, if it was a negative correlation, when you had less of that parameter, you get more of the bats. So your job is to look at this here and try and figure out which of these parameters matters. And not just which matters, but how confident are you of that? And these error bars on either side here represent the confidence interval of this correlation coefficient, meaning they think it's probably where the little diamond is, but it could also be somewhere along this range. There's a probability, and if these are 2 sigma error bars, that would be, there's a 95% probability that it's somewhere along this range, with the highest probability being in the center, but you can't be sure that it's not out over on one of the limbs. So which of these things do you think matter? And you can pause the video and stare at this a little bit. Well, the first one I think that stands out the most to me is our days since the rice planting, and that on the black-bearded tomb bat. That diamond is over here on the left side, and there's a gap in between here, meaning that this is statistically different from 0. It's very unlikely that it doesn't matter, and it's very likely that there's a negative correlation. So that means that the farther you get from rice planting, the fewer bats are around, at least of the black-bearded tomb bats. That does not seem to be true so much for, say, the Java pipistrelle, where it's basically the diamond's very close to 0. And the bent-wing bat maybe has the same trend as the black-bearded tomb bat, but it also could be, it overlaps with 0, so it could be unimportant. The next one that you see on here is one that definitely makes a difference, is the playback. When there is no playback, that means that there are more bats of the Java pipistrelle. That does not seem to be true of the black-bearded tomb bat. So why would it be that the black-bearded tomb bat seems to be unaffected, the correlation coefficient is 0, whereas the Java pipistrelle bat is negatively correlated? It avoids the playback, and the black-bearded tomb bat doesn't seem to care either way. Well, if we go back here to look at this, the black-bearded tomb bat has its sounds that it makes for echolocating on the low end of the katydid spectrum. In fact, some of their calls are in fact outside of the katydid calls, and even where they do overlap, they're overlapping at a lower amplitude than, say, the Java pipistrelle bat, where their entire signal is within the range of the katydid noise, and so they can't hear their echolocation calls nearly as well because of all that noise right in the same thing. And the bent-wing bats are somewhere in between. They're kind of over off to the edge. They're at a lower amplitude than, say, the Java pipistrelle. The katydids don't make quite as much noise in the frequency bands that they care about, but there is some overlap there. And so when we actually go and look at their response to the playback, we see it seems like they also don't like the noise. They also avoid the noise. But it is a slightly less confident answer because it's almost overlapping with 0 here. With the one caveat that we should make note of is that they changed the scale down here at the bottom, so all 3 of these are at different scales, and I think that's a little bit unfortunate and misleading for us when we're trying to compare them side by side. It turns out that this effect here, if you look, here is the line for 1 or -1, and the bent wing bat, the correlation coefficient is pretty close to -1, whereas -1 on this graph is all the way over here. And so, visually it's hard to tell, but you could actually argue that the bent wing bat is more affected by the noise than the Java pipistrelle, although we're not entirely quite as confident because of the fact that the error bar almost intercepts there. So we're really seeing that the noise of katydids affects bats. Let's scroll down to our next couple questions here. The next one is, to what extent does artificial light affect bat activity, and should this be taken into consideration when deciding on placement of bat detectors? What a wonderful question. This would be a perfect research project for our class where you could test that out. It's very easy to test out. You just find some place where we've got street lights in one spot and put a microphone near the street lights, and then go someplace a little bit further away that does not have the street lights, and see if you get more bats around one of those than around the other. So a great question. I hope somebody will answer that in our class. The last question we're going to address today here is, are there any annoying animals that either coincidentally or purposefully perfectly mimic a bat's call and call behavior? Well, we saw that the katydids, they're not at all a perfect mimic to a bat's call because they create these constant drones of noises at bat-like frequencies, but they are overlapping in frequency that's really important. And so I just wanted to try. So even though the answer is no, there's nothing that's an exact mimic of a bat because nobody else needs to echolocate like bats do, there are a lot of animals that have overlapping frequency ranges with bats. And we last time looked at how katydids affected bats. I want to just look at the flip side of the coin while we're thinking about other organisms and sounds in that frequency range. Do bats affect katydids? And there was a cool study that was done, I think this one's in the Philippines, and they looked at comparing what happens to the sounds of katydids before a bat pass versus during versus after. And so, what they do is they start off with before the bat pass, they look at the katydid noise and they sort of use that as a baseline. And then they check and see, when bats are flying over, do the katydids make more noise or less noise? And then after the bats are gone, do the katydids get really excited and celebrate and make lots of noise, or do they quiet down, or what's going on, and how are they affected? And so let's go ahead and take a look at the results. The first thing that they wanted to do is they wanted to just show us what happens when there's no bats present. And let's just see how much katydid noise varies from moment to moment. So 2 random time points they just took that were a couple seconds apart just to see. And these graphs here show frequencies in kilohertz on the horizontal axis, and then the amplitude change. So getting louder is above the 0 and getting quieter is below the 0. And you can see that in some frequencies they get a little higher, some frequencies they get a little bit lower. You can kind of see the scatter that you might expect for this species of katydid and how much noise varies from one time to time. So if we see changes that are kind of within that same range, we say, that doesn't seem like a very convincing change of katydid behavior. But if we see these little dots starting to go way down here or way up here, then we know that there's actually a real signal that the katydids are affected by the bats. So let's find out. Here's the results from during a bat pass. And if we look at the frequency content, we see there's a whole bunch of energy here at frequencies in the 20 kilohertz and then again around 40 and 60. And that shouldn't be surprising because this is during a bat pass. And so the microphone records both the katydids and the bats. And so these are the 3 different, there's 3 different species of bats that they're typically hearing, or 3 different categories of frequency ranges here. So we see that increase in energy from them. But down in these other spots, we do see some drop, including some pretty big drops here. And the red stars are places where they have identified that these are statistically significant drops. So there are places where the energy is definitely less. So when a bat comes by in some important frequency ranges, the katydids get quieter. And then after the bat has gone away, even a few seconds later, they stay quieter. And again, some of this is not statistically significant. A lot of this stuff in here is not. Out in this range, they identified it as sort of marginally statistically significant. It's tantalizing. It seems to be in the right direction, but they need a few more nights of data before they would really be able to confirm that. But even over here, we're definitely seeing some pretty strong quieting down of the katydids. So do bats affect katydids? Definitely, they do. The katydids seem to quiet down. And why might that be? Well, there are certainly some bats that might eat katydids, that might come down and glean them off of leaves, picking them up off the leaves, and so they don't want to get eaten. So when they hear a bat, they quiet down so they don't get eaten. This seems to be the best interpretation of this. We were working a lot with amplitudes in there of the sound. And so we're going to come back now to the time when we went out inside and we recorded using our little dog bark repeller ultrasonic generators. And we went and stepped further and further away and we recorded how loud they were with our microphones. This is our data here. And the time of recording relates to the distance because we kept walking away from the microphone. And it gets quieter and quieter and quieter. And we're going to look at that in detail. We're going to quantify how much quieter. So we need to understand, how do we measure the intensity of sound? And you've probably heard about the decibel scale here, where there are these numbers. They go, down from low ranges of zeros down up to a car might be 70 decibels, a conversation at 60 decibels, a jackhammer is 100 decibels. If you go to a rock concert at 110, it starts getting really painful around 130. So there are these numbers here, but what exactly do they mean? We need to put this in perspective, and one of the things that previous diagram doesn't really articulate is that those decibel levels are for a certain distance away, and they're all unequal distances. This is not quite a fair thing, like a passenger car at what distance, if you're right next to it versus with your ear like up against it, or versus, as it's passing you by on the street. And I think they're intending, as it passes you by on the street. And a jackhammer, again, if you're right next to it, it's going to be very different number of decibels than if you are a little bit further away. So something that I have found is, consistent is that if you measure a smoke detector from 10 centimeters away, and how loud is that? That's 108 dB. Versus, say, a bat can be up to 130 dB at that same distance of measured away. So very loud. Bats make a lot of noise. But as you get further away from the bat, it gets quieter. That makes sense. As you walk away from the microphone, it gets quieter. But how much quieter? And so what we need to know is that as a bat sends out energy, it spreads out in all directions, or sometimes a little bit unequally, but it does spread out in all directions. And that bat is delivering a certain amount of power that gets spread out over the whole area that the energy is going. And that area is, if it's spread out in 3 dimensions, it's a sphere. And so we need to think about the area of a sphere, and that's going to become really important. And if you are at a certain distance, like the radius r0, r0, oftentimes in formulas we're going to see the initial value that we use. We put a little subscript 0 next to a variable so that we can indicate that's sort of our initial value. And we might change that to a different value and go further away and see how much does the intensity differ between those two distances. And bats you don't have probably quite as much personal experience with, but let's give this example of you at a rock concert and you are standing a certain distance away from a speaker. Well, it's really loud. How do you get it to go quieter? You go further away from the speaker, and we want to know how much does the intensity go down as you go further away. Like, if you start off a meter away from the speaker and you go 2 meters away, is the intensity half as much? Well, we're going to have to try and figure that out. It has to do with the power That's going to stay the same. The power of the speaker is always the same. And the area that energy is spread out over. And that area varies based upon the surface area of a sphere. And I've sort of illustrated that here, or stole an illustration off the internet of this, where we see that the area that is spreading out and spreading out and spreading out. And so as you get further away, the energy gets spread out over a larger area, which means that it's going to have a lower intensity. So let's calculate it out just in variables for a moment. So our intensity is I, and if we wanted to figure out I naught, the intensity from this first little shell here where we were close to the speaker, we need to come up with the power divided by the area. And the power we're just going to say is the letter P. And the surface area of a sphere is 4 pi r squared. Well, our r in this case is not r, it's our initial radius r naught. So we're going to take that 4 pi r naught squared. And that's going to give us intensity at this first shell. If we go out further away, the intensity is going to follow that same thing. It's still going to be the power divided by the area. The power is the same, it's the same speaker, but the area is going to be different because we have a different r. So that's going to be power divided by 4 pi r squared instead of r naught squared. R naught is the distance away for the first little shell, and r is the distance for the second shell. So we have those two, and we kind of want to know, this question was how much louder? So how much louder? If, is it twice as loud? Well, how do you figure out whether something's twice as big as another? Is you divide them. It's simply the intensity at this outer shell divided by the intensity at the initial baseline place where we were standing when we started. So to do that, we can just take these numbers that we have here and we can put them on top and on bottom of a fraction here. So we got our intensity, that's the one with the r in the bottom, and the intensity naught is the one with r naught at the bottom. And I see this here and I can start simplifying things. I love simplifying things. What do? If I have the same thing on the top and the bottom of a fraction, what do I get to do? I get to cross them out. And then here I now have the denominator of this fraction and the denominator of the other fraction. They both have 4 pi, so I can cross those out. And so now I have this r naught at the bottom of this and the r squared at the bottom of that. And when I'm at the bottom of the bottom, I get to bring things up to the top. That's a feature of dividing fractions, as you multiply by the reciprocal, and so you end up at the top. And so this simplifies to the intensity over intensity naught. How much louder does it get is going to be equal to r naught squared over r squared. And we could just use one more property of fractions that could be helpful to make it look a little bit simpler. Sometimes it may not be simpler, but you can take r naught divided by r, calculate that out, and then take that whole quantity and square it. And these two things are the same. So this is a useful way to depict this. So let's give it a try. Let's try and see how much louder is an airplane engine when you are high overhead, like 1,000 meters away. You can hear that airplane engine, right? Compared to if you had your ear 1 meter away from that airplane engine. How much louder is it going to be? Well, we'll take our little equation, I over I naught, and we're going to calculate r naught over r and square it. So our initial distance away is going to be 1 meter. So that's r naught. And our new distance is 1,000 meters. So 1 over 1,000, and we have to square that. So when you square something, you multiply it by itself. So 1 times 1 as multiplying across the numerators. Remember how to multiply fractions? You got to multiply the numerators, and then you multiply the denominators. So 1 times 1 is 1. And then 1,000 times 1,000 is 1,000,000. So the intensity is 1/1,000,000th as loud when you're this far away compared to here. So way different, 1,000,000 times different intensity. So these numbers are getting pretty big. So some way that we can make this a little bit simpler, to instead of writing so many zeros, is we can use the log base 10, and we can take our quantity I over I naught, or r naught squared over r squared. Those two things we determined were equivalent. We can take that ratio, and we can just take the log base 10 of that. And so just to remind you about log base 10, how that works, it's essentially saying how many zeros are there, or what do you have to raise the 10 to the power of in order to get there. But that's, with these simple numbers that we have, it's always how many zeros are there. And so the log base 10 of a million is 6, because 10 to the 6th is 1 million. For 1,000, the log base 10 of 1,000 is 3. It's got 3 zeros. 10 to the 3rd is 1,000. Log base 10 of 10, you might remember that that's 1, because 10 to the 1st, the first power of 10 is 10. This one here, you might also have to remember the log base 10 of 1. How do you get 1? Well, you multiply 10, or not multiply, you raise 10 to the 0th power, and that is always 1. Raising anything to the 0th power gets you 1. And then, interestingly, what happens when you go to smaller numbers than 1? Can you get smaller than 0 for dBs? Ah, look at that. You get -2 here for log of 0.01, because 10 to the -2 is 0.01. So this is almost what the definition of a decibel is. But when they were first developing this, when they were using this to try and figure out how much energy loss there was over running signals through telephone wires, they were looking at the intensity that they put in to a telephone wire at one end, and then how much energy came out at the other end. They were saying, oh gosh, we're losing some energy, because that happens with electricity, with electrical loss. So how much is that? And they did that out, and they're like, gosh, these numbers are really small. Like, it's 1 million times loss in energy, and we're only getting, dBs of 6. So what would happen if we just added a factor of 10 in there? So that becomes 60. And that was really cool, because what they found was that that loss of 1 dB turned out to be equivalent to about how much energy was lost when they ran a telephone signal over 1 mile of standard telephone cable. And that was the type of calculation they always had to do, was that if you had, how much loss will there be over 10 miles? And so they would be able to simply say it's 10 dB. And this was working beautifully for them when they added this 10 in here. So this is the equation that you have for dB, and it's the factor of 10 is purely just. They just decided it would look better if these numbers would be more interesting to look at, and if they just multiplied it by 10, and that's how they defined the decibel. So it's not like it's something physical, and there's a fascinating history of this in this article down here. So we can try this out. You can see that dB equals 10 times log base 10 of r naught squared over r squared. Fun fact with logarithms, I don't know if you remember that you can pull out the exponent from inside the log and make it into a coefficient. So you can take that 2 out and multiply 2 times 10 and you get 20. So you can kind of simplify that there. And you can quickly try and see how well this works here compared to 1 meter away. How many dB lower would you expect at these different distances? And so you can calculate that out for a couple of them. Go ahead and try that. And you should hopefully start seeing here that at 1 dB, the number is 0, because it's exactly the same. There's no loss when your reference distance is 1 meter and you are standing 1 meter apart. It's the same, so 0 dBs. By the time you get to 2, you're at -6 and -9.5 and -12. So what we did in class after we've done this here is we actually went ahead and did this in R. We've coded in, making an array from 1 to 20, calculating the dB, and plotting it using this. So you can work on that as your first exercise in R. So that's what it looks like in theory as you get farther away. But we actually did this in our class. We took our little dog-repelling ultrasonic generators, these little things that we pushed a button and it made a noise, and we went out and we put our dog repeller right close to the microphone, and then we started walking away, and it got quieter and quieter and quieter and quieter. And we have this recording of this. So what you're going to do is in R, you're going to load this wave file in there, and you're going to create spectrograms of each one of these little pulses, you're going to focus in on one pulse at a time. So you're going to draw a very small spectrogram that's going to be around the pulse as right here at the beginning and end of this pulse, and over a very narrow frequency band. So we just look in that little area right there, and you're going to say, generate that spectrogram, and it's going to look like this. And it's going to show you the colors of that spectrogram correspond to different intensities, and you could read off what's the maximum intensity of this pulse. Well, that one looks like it's close to 60 dB. And then you'll go to the next pulse and do the same thing, generate a spectrogram there, and that one there, well, that one looks like it's closer down to the 40s range. And then you can go all the way one by one until you get to there, and you can see this one, ooh, this one's starting to be in that 20 dB range. And so you'll be able to come up with those and then map those to distances and make a plot of amplitude versus distance, or sound intensity versus distance, and see how the intensity drops off as we take different distances. We have a plot kind of like that right here of what we think it should be, but what does our data actually show? And so to do this, it turns out that actually you're not actually going to be looking at these spectrograms and reading off numbers from the color scale. Once you create a spectrogram, you can store it in a matrix, and you can actually ask R to report to you what's the maximum value, what's the maximum number, and you can get that and store it into an array. So you can keep doing that, and you'll have the first one in the first element of the array, the second one in the second element array, then third, fourth, fifth, sixth, all the way out to, as many as we have. I think in this particular file, I believe there are 11 of them here, and I think we decided this third one is a glitch, so don't worry about that one. And so you're going to code that into R, and I've given you the structure to do that. If you download our file in Canvas, the starting point and the actual data files are there for you.